Welcome to the lecture on matched or paired samples. So coming off the heels of independent samples where we compared means and proportions, this one is going to be a little bit different because we're going to have them have a before and after feeling. So a test for the comparison of two sample means depends on the samples being independent or dependent. And we kind of have to make that determination straight away. So when we did independent, right, the two samples weren't affected by each other. And then we also said we could have mismatched sample sizes. Meaning you could have something like N1 not equal to N2. That was fine because they were independent samples, and so I didn't need to have them pair up perfectly. For dependent samples, I want you to think of it, and this is not the hard and fast definition, but I just want you to get in your head that this should be like a before and after. And you do need matched sizes. Like you can't have one set of information have 19 values and the other set of information have 20 values, because it's really like one category looking at it before and after. So you should have 19 in both. Okay, so if the samples are dependent, then we need to make sure that each sample has equal sample sizes. That's what we just said. And then if the samples are independent, I love being redundant in the afternoon. We do not require equal sample sizes. All right. So let's just see if we can figure out if some things are dependent or independent. So in the first example, we're going to randomly choose 5 men and 6 women and compare their heights. So this is going to be independent. The first tip off is that we don't have matching sample sizes. And also the height of men doesn't really affect the height of women. So this is going to be independent. Certainly 5 is not equal to 6. And the height of men does not affect the height of women, nor vice versa. In example 2, choose 10 men and weigh them. Give them a new wonder diet drug and then later weigh them. This is a classic case of dependent. It has that before and after feeling to it. And then the last one, take 10 people and measure the strength of their dominant arm and their non-dominant arm. And this is also dependent because certainly the dominant and non-dominant arms kind of affect each other. Like you wouldn't expect like a guy with gigantic biceps in his dominant arm to then have like the teeny tiny chicken arm. He's probably generally strong all over. And granted, he might be stronger in his dominant arm, but like you don't get one massive quad and then like one totally atrophied quad. There's an effect there. There's a dependence there. Okay. So the required characteristics and conditions we need are a simple random sample. Of course, we always need simple random sample when we're doing statistics. Well, we need to compute the differences from each pair. So like in the case of the dominant arm and the non-dominant arm, we're going to take person 1 and we're going to measure the strength in both of their arms. And then we're going to look at the difference between that strength. So let's say like, for example, that guy can curl, I don't know, I'm totally making this up, 20 pounds in his left arm, but he can curl 30 pounds in his right arm. And so the measured difference there would be 10. And I want to do that. I want to measure the difference for each person I go through. This is different than when we did our independent sample because I would have done the average of the non-dominant. Then I would have done the average of the dominant and I would have just gotten one difference in the averages. Here, I'm getting the difference each time and I'm averaging the difference. So that's the second bullet point. Differences are calculated from matched pairs or samples. So this is going to be D for difference. And then what I'm going to do is I'm going to take the average of all these differences. That will be D bar. This is going to be the mean of the sample differences. And either the matched pairs have differences that come from a population that are normal, meaning like we have that given to us in the problem, it says that, or I have a sufficiently large number, at least 30. And this is an assumption that we've seen, I want to say a million times, but I'm being hyperbolic. We've seen it a lot. All right, so to set up our hypothesis test, we want to state the random variable in words. So the random variable is going to be the difference which we said was given by a lowercase d of each pair, right? So again, think of just the one guy. He's got two arms. One is a dominant, strong arm, and the other is a non-dominant, probably weaker arm. And I'm going to measure the difference in how much he can, I don't know, bicep curl or something. And that measurement, that is a outcome for the random variable. And I want to do that for everybody. The null and alternative hypotheses. Okay, now we're going to change things up because in the independent samples case, we always assumed that there's no difference, that mu1 is equal to mu2 or p1 was equal to p2. In this case, we don't necessarily have that. There's going to be a lot of times when we assume that it's 0, but it's not necessary. So the null hypothesis is always going to be mu d. So again, mu for mean, population mean, little d for the difference. So this is really going to be the true population mean of the differences. So if I had every single guy and made him do a bicep curl on both arms and I had every single difference, then I could get the true population mean of that difference. We're going to be using samples because we're doing inferential statistics and hypothesis testing. So we always default to equality, and it's going to be some number, not necessarily 0 this time. And then the alternative hypothesis is you have mu d, this number, and we have to make that choice, right? Like it's going to be greater than, less than, or not equal to, which is going to give us right tail, left tail, or two tail. This is not new information. All right, state the level of significance. So if alpha is not specified, we'll continue to use 5%. We always want to check our assumptions. And then, right, we need to either be normal population or our sample size needs to be at least 30. And then we're going to compute our test statistic and our p-value. So of course, if p is less than alpha, then we are going to reject H naught. And we have enough evidence to support the alternative. Whereas if p is greater than alpha, then we fail to reject H naught, and then there is not enough. Oops. To support the alternative. All right, so let's see if we can crank out some examples. A survey of 41 people, okay, boom, there's N straight off the bat, was conducted to compare their self-reported height to their actual height. And the difference, D, between reported height and actual height was calculated. You're testing the claim that the mean difference is greater than 1.1. Okay, so here is where we're coming into our null and alternative hypotheses. You're testing the claim that the mean difference is greater than 1.1. So if I set up let's set up our alternative first. The mean of the differences is greater than 1.1. This is a right-tailed test. And we know that for our null hypothesis, it's just going to use equality and we have the same number. So we can see here already that it doesn't necessarily have to be that the difference is 0. Okay, our sample mean, D bar, the sample of all the differences, sorry, the mean of all the sample differences is 1.15. The standard deviation of the differences was 0.5, and we said that the sample size was 41. So now I'm gonna go over to Excel and input it and see what I get for my test statistic and for my p-value. Okay, so once I'm in Excel for matched pairs, I have 2 roads that I can choose. I can either put in raw data, and this should feel familiar to when we had independent means. I can put in the raw data and it'll crunch out the difference for me, take the mean of the sample differences, compute the standard deviation and the sample size. That's great. Or I can give it what the sample mean is. And so we weren't given raw data. We were just given the sample mean. D bar was 1.15. The standard deviation for the sample was 0.5. And we know that the sample size was 41, which means we met our assumptions. If I have information in both places, all of a sudden I'm going to get this error for data overlap. So just make sure you're using one or the other. And as always, if it's not a pink box, don't change it. Don't delete it. Don't write in it. Leave it alone. Okay, so I also need to give it my alpha. So I think alpha is going to be 0.05 for 5%. And I also need to give it my null hypothesis. So the null hypothesis used the value 1.1. And now I'm all set. So I'm actually going to move this over to OneNote so we can digest information. So there's a lot of ways you can look at how to reject or fail to reject. We use the p-value. You could have also used critical t-scores, meaning that like what we're really saying here with critical t-scores for a right tail, it's saying, hey, you can be no further away than 1.684 standard deviations. But if we look at our test statistic, we're only 0.6403. So it's like mom saying like, hey, you can go 2 blocks away from the house, but no further. And you're just like, no, I'm just going to go to my friend's house 1 block away. You're not in trouble. Everything's fine. It's kind of what happened here. We're not so far away that we're out of the ordinary. And typically we just look at the p-value. So for right-tailed, our p-value was 0.2628 and our alpha was 5%. So certainly p-value is bigger than alpha, and we're going to fail to reject H naught. So we don't have sufficient evidence to support the claim that the true difference was actually larger. Okay, in this next example, we're given actually raw data. So a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown. A lower score indicates less pain. And the before value is matched to an after value, right? We have that in the table, and then the differences are calculated, which will make Excel do that. But just for grins, what it's doing is it's saying, what was the change from before to after? This was plus 0.2, right? Because 6.8 minus 6.6 is 0.2. And so here we saw that the pain went up. So that's not good. That's not what we want. But let's look at this next one. So this is going to be 2.4 minus 6.5, right? So this should be negative 4.1. So in that case, the pain went down. And I can actually do this for all of these. And what I'm going to do is after I get all of these, then I'm going to take the average of all of these differences. That becomes D bar. That's our sample mean. And we're going to compare that to our null hypothesis. So what is our null hypothesis? Are the sensory measurements on average lower after hypnotism? Did pain go down? All right, well, for this one, let's just set it up like this. We're going to assume that did pain go down means that mu D is less than 0, right? So look at the first for subject A. Pain went up, our difference was positive. In subject B, pain went down, difference was negative. So we want to test whether or not pain went down. That would mean that we have a negative difference. So my alternative hypothesis is mu D less than 0, and my null hypothesis is just using that same 0 and then flipping the sign in between to equality. So I still need my D bar. I need SD, and I need my sample size. And when I have raw data, I'm actually going to let Excel calculate all that for me. I'm given a significance level of 5%. So let's plug this in and see what we get. So I want to share something really quickly. Once I plug in my data values, we'll notice that in gray, I'm going to get all my differences. And then over here in the from data box, it's going to give me my sample mean, my standard deviation for D, and my sample size. And that should all work out. I'm going to change my null hypothesis to 0. But even though I have all this information filled in correctly, I'm getting this error. It says data overlap, data overlap, data overlap. And the reason for that is because I haven't cleared out my data from the previous problem. So you're either going to have raw data on the left from the table and stuff in gray, or you're going to have your data from your given information. Not both. So as soon as I get rid of that, everything's fine. And now I can digest and decide. So now that I have everything here, I have my 5% alpha, I have my null hypothesis of 0, I have my raw data, my sample values with standard deviation and sample size, and I know I'm using a left-tailed test. And that's how I'm going to decide on whether or not, or on what p-value I'm going to use. So my p-value is 0.0095. Alpha was equal to 0.05 and p-value was less, so I can reject the null hypothesis, and I have evidence to support the claim in HA, meaning that I have enough evidence to show that this hypnotism actually does reduce pain.